Hello dear students, Assalamu alaikum. I hope you will be fine. My name is Engineer Mir Masood Shah. I am lecturer in Department of Technology, Sarhad University of Science and Information Technology, Peshawar. As I am teaching you the subject Fluid Mechanics, today is your lecture number 13. In lecture number 13, we will study about Orifice Meter, which is one of the application of the Bernoulli's equation. So an orifice meter is used to measure the discharge in a pipe. So whenever a liquid is flowing in a pipe, in order to measure the discharge of that liquid in that pipe, we used orifice meter. An orifice meter in its simplest form consists of a plate having sharp-edged circular hole known as orifice. As you can see in the figure, this is the circular plate which consists of sharp edges, having sharp edged circular holes, and this is known as an orifice. This plate is fixed inside a pipe as shown in figure. As you can see, this plate is fixed inside the pipe, and this circular hole is known as an orifice. A mercury manometer is inserted to know the difference of pressure between the pipe and the throat, that is orifice. So this is the differential manometer which is inserted in order to find the difference of pressure held between the pipe. This is the pipe and this is the throat. This orifice is known as the throat of the orifice meter. Let H is equal to the reading of the mercury manometer. This is H. This is the reading of the mercury manometer. P1 is equal to pressure at inlet. V1 is equal to velocity of liquid at inlet, and A1 is equal to area of pipe at inlet. And P2, V2, A2 equal to corresponding values at the throat. Now applying Bernoulli's equation for inlet of the pipe and the throat, so Z1 is equal to Z1 plus V1 square divided by 2G plus P1 divided by omega is equal to Z2 plus V2 square divided by 2G plus P2 divided by omega. As we know, this is the equation of the Bernoulli's equation. Here, as the pipe datum is on the same level, so Z1 equal to Z2, so they will cancel out with each other, and we get P1 divided by omega minus P2 divided by omega equal to V2 square divided by 2G minus V1 square divided by 2G. Or as we know, P1 divided by omega minus P2 divided by omega is H. So H is equal to V2 square divided by 2G minus V1 square divided by 2G. Take out 1 over 2G as common, so we get H is equal to 1 over 2G into V2 squared minus V1 square. Let this is equation number 2. Now since the discharge is continuous, so therefore according to equation of continuity, A1 V1 is equal to A2 V2, means the discharge at point 1 equal to the discharge at point 2. So from this, V1 is equal to A2 V2 divided by A1. Taking square on both sides, we get V1 square equal to A2 square V2 square divided by A1 square. So put this V1 square in equation 2, and we get H is equal to 1 over 2 V2 square minus A2 square V2 square divided by A1 square. Now take out V2 square as common, so we get H is equal to V2 square divided by 2G into 1 minus A2 square divided by A1 square. Now take LCM, so we get this V2 square divided by 2G into A1 square minus A2 square divided by A1 square. Now take out the value of V2 square from this equation. So we get V2 square is equal to 2GH into A1 square divided by A1 square minus A2 square, or taking under root on both sides, so we get V2 is equal to under the root 2GH into A1 divided by under the root A1 square minus A2 square. Now we know that the discharge Q through an orifice meter is equal to coefficient of the orifice meter into A2 V2. So here put the value of V2 from the above equation. So we get Q is equal to C A1 A2 divided by under the root A1 square minus A2 square into under the root 2G H, where C is the coefficient of the orifice meter. So this is the final equation which is used for finding the discharge through a pipe by using an orifice meter. Now we will solve an example on this. So coming to example, the statement of the example is an orifice meter consisting of 100 millimeter diameter orifice in a 250 mm diameter pipe has coefficient equal to 0.65. So the diameter at the throat or at the orifice is 100 mm, while the diameter of the pipe is 250 mm, and the coefficient is given which is equal to 0.65. Now the pipe delivers oil having a specific gravity 0.8. The liquid in the pipe is oil and a specific gravity is given which is equal to 0.8. The pressure difference on the two sides of the orifice plate is measured by a mercury oil differential manometer. If the differential gauge reads 80 mm of mercury, calculate the rate of flow in liters per second. So the mercury differential gauge is also given which is 80 mm, and we have to calculate the rate of flow in liters per second, means we have to calculate the discharge in liters per second. So in solution, first of all we will write the given data. In given data we have D2 is given which is equal to 100 mm, which is equal to 0.1 meter, which is the diameter of the orifice or the throat. D1 is equal to 250 mm, which is equal to 0.25 mm, and this is the diameter of the pipe. C is the coefficient of the orifice meter, which is equal to 0.65. Specific gravity of oil is already given which is equal to 0.8, and H is already given which is 80 mm. So this will equal to 0.08. This is not 0.8, this is actually 0.08 meters of mercury. This is the H is equal to 0.08, as it is 80 mm of mercury, so H is equal to 0.08 meters of mercury. Now we know that the area of the pipe A1 is equal to pi by 4 D1 square. So put D1 is equal to 0.25. So you will get the area A1 which is equal to 49.09 into 10 raised to power minus 3 square meter. So this is the area of A1. Now calculate the area at the throat or at the orifice. So that is A2 is equal to pi by 4 D2 square. D2 is equal to 0.1. So A2 comes out to be 7.854 into 10 raised to power minus 3 square meter. So this is the value of A2. Now we also know that the pressure difference H is equal to 0.8 into 13.6 minus 0.8 divided by 0.8. Here the calculation is is done with 0.8. So in here take this value is 0.8 and also make it 800. So in that way our calculation will be fine. So this is not 80, in fact this is 800. So H is equal to 0.8 meter. Here it is correct, as the rest of the calculation are taken are done with 0.8 meters. So here make it instead of 80 it is 800 millimeters of mercury. So then H is equal to 0.8, which is this is the specific gravity of the oil, and this is this is the mercury head, which is already given in the statement. H is equal to 0.8. This is 13.6 is the specific gravity of mercury, minus 0.8 is the specific 0.8 is the specific gravity of oil, and this is divided by 0.8 is also the specific gravity of oil. So by subtracting the specific gravity of oil from mercury and dividing it by specific gravity of mercury and multiplying it by the mercury head, you will get the pressure difference H is equal to 12.8 meters of oil. Now we know that the rate of flow, that is Q, is equal to CA1 A2 divided by under the root A1 square minus A2 square under the root 2G H. C value is already given, which is 0.65. A1 A2 is already calculated, so put the value from there. G is 9.81, H is already calculated 12.8. So put all the values, you will get the value of Q, which is equal to 82 into 10 to the power minus 3 cubic meter per second. So multiply this by 1000, you will get this value in liters per second, and Q is equal to 82 liters per second, or the rate of flow, that is Q is equal to 82 liters per second, as 1 cubic meter is equal to 1000 liters per 1000 liter. So we convert this cubic meter into liters per second, and we get the value of 82 liters per second. So this is the end of our lecture number 13.